And with this, it builds us confidence into the data set that we are generating. So it is not only a matter of seeing if the image looks similar or not, it is also knowing, because once you create 10, 50,000 images, you're not going to check every one of them, right? So what you want to do is you want to know that the parameters that you have will create realistic patterns.
Welcome to a new episode of our inVISION podcast, 5 Questions To. Our topics are image processing, machine and embedded vision, AI and metrology. My name is Peter Ebert, Editor-in-Chief of inVISION, and I'm happy to have you here for a new episode. The possibilities of synthetic data for AI vision or digital twins are diverse. Therefore, in today's podcast episode, we have invited Petra Gospodnetic, who works on the topic of inspection planning research at Fraunhofer ITWM, and Maximilian Grau, CEO and co-founder of Medabsy, to tell us a little bit more about synthetic data and the upcoming cooperation of both partners. Hello, Maximilian. Hello, Petra.
Hi.
Hello.
My first question is, what are synthetic images and what kind of benefits are they bringing to machine vision industry? Maybe Maximilian, you will start to answer?
Yes, also synthetic images, we see it on the context of digital twins. And first I want to say, digital twins for machine vision are digital representation of a real system that have nearly the same physical behavior as the real system, and where you get easy a synthetic photorealistic image from the camera perspective. And the advantage is that there are many advantages with simulations and synthetic images. But in my opinion, the 3 most important benefits are, first, you can faster test which hardware do you need to solve your machine vision challenge. Normally, you have to test in a laboratory which system you need. This is called feasibility studies, which consumes a lot of time. With digital twins and synthetic images, you will digitalize the process and saving a lot of time. This is really important for people who are designing this inspection system, but also for people who are selling optical components, because they don't have to set up the real hardware, and they can show the customers, with the simulation, how the synthetic or how the image will look like with these components. The second benefit is you shift your working hours from the machine to the office, because normally an application technician or engineer time is most expensive when they are working on the machine, especially when the machine is already at the end customer. With a simulation, you can do a lot of work in your warm office and prepare your work on the machine before you go to the loud and cold factory. So it means that the working time in the office increases a little bit, but here the costs are really relatively low. So this is also the reason why I think it's simulation and synthetic images is really is something where managers and project planners for machine vision has to think about it. And the last benefit, one of the biggest, is with synthetic images, you can boost your machine vision, your AI, if you're using AI as a software. Because with synthetic images, your AI is more reliable. So the most projects lack the right data and the right amount of data. It's impossible to get, or it takes a lot of time and effort to prepare. With synthetic images, it's really easy to change your target because everything is parameterizable. So you can create a lot of different variations, such as different materials, colors, scratches, cracks, everything. So, and this synthetic images, you get also pre-labeled. These are the most, biggest benefits.
Oh, thanks. Petra, what kind of synthetic data approaches exist today, and what should users consider when choosing the right approach for them?
Thanks, Peter. That's a great question. So the thing is that today we can witness really abundance of different approaches, and people use different terms from different tools, and those very often get mixed. What one can think of 3 basic types of synthetic data first is the data augmentation. That one has been around for a very long time, and it typically involves in painting or performing rigid transformations on images. So having already a data set that can be augmented to show more different features, but it's based on a data set that exists. We can there also see combination of, for example, if we're talking about inspection, surface inspection, combination of defects that have been found in other places or images, and then in painting them into existing images. The issue there is, well, you will definitely have a more general data set. The issue is you don't have really the control over the environment under which both data sets have been created and then combined. So the in painting will not necessarily be physically consistent, and also it is very difficult to perform this in a seamless manner that would make really the network more robust. So it has definitely shown to be useful, and it is a standard practice, I would say, in almost every machine learning training pipeline to perform data augmentation, but that was one of the first ones. Then we have the rule-based simulation approach, and we have generative AI approach. And those are the two main approaches actually of the synthetic data today. Now, one that we hear a lot about is generative AI approach, which means you have a small data set that you use to train another machine learning model. And this machine learning model is then dedicated to create more data for you that you can use then further on for training. That is one approach. It is a very popular one because it is, I would say it is often popular because it is developed by machine learning developers for machine learning developers. So it is easier to develop something that you're already very familiar with. And it sounds rather easy because it consists, so it's based on training. It's based on saying, okay, we have enough data, now we have to train it. And it doesn't require necessarily so many complex parameters inside. The problem is there, the question of controllability. So if we are using generative AI to create data sets because we are actually missing data, then a natural question arises. If you're already missing the data, how do you expect to train your data set generator? There are multiple ways that one can tackle that, and there are multiple things that have been done in this region, but this is always a question. Second question is very often, how do you control the labeling? So one key point of synthetic data is that you have labels that are automatically generated together with the synthetic data, which is a key benefit because it avoids the labeling process, which is very tedious. Now, there the question is, okay, how do you make sure that you have the labels and that the labels are correct? And very often we can see that the generative AI struggles with having pixel-precise labels. There are, again, methods to avoid this, but they are not as easy as one would say, okay, we just train it and we get the synthetic data with the labels. So they are very, very complicated systems. And another thing is often question of the resolution, where you are rather limited with the possibilities of the resolution and what you can generate, of course, on the hardware, on the processing and computational capacities. And then finally, we have the rule-based simulation. Rule-based simulation is, the concept of rule-based simulation is that it uses physical simulation and rules of the environment under which the image is created. So in case of image simulation or visual image simulation, we are typically talking about light transport simulation. And there you can control all the parameters you need and all the parameters that are influencing the acquisition process and imaging process. Yes, it is more complex. However, when one has all the right algorithms and the models, and when I'm talking about models, I'm talking about mathematical models. When one has the right mathematical models, you can completely control the data set. You know exactly what you're defining, so you know exactly what you're generating. The data sets are balanced. Pixel precise labeling is not a problem. You have no limit in resolution of any kind. And what is very interesting is you can completely control the size, the variation of your data set, and most importantly, the edge cases. So one thing that what you can do in rule-based simulation, which is extremely difficult to do in other ones, is the out-of-distribution simulation. That means you have edge cases that can appear on your production line. There is no way to simulate them with a model that simply repeats what they have seen so far. You would have to blow up your production line to get the edge case scenario, and then to have this very small specific training example to try and train the model for that. If you're using rule-based, that is also only a question of parameterization. So I personally see rule-based as a very important branch of synthetic data generation. And for sure, in the future, it will have a rather big role in the industrial synthetic data generation.
Thanks. Another question. What do you think? How realistic is synthetic data today? And how can I know that a synthetic data set will work for me?
So that is always the question. That is a question which I very often get asked by my customers or partners. And it's interesting. So when we're talking about generative AI, there are metrics that are measuring realism. However, do not be deceived by that, because those metrics are actually relying on scores that have been trained or natural images. We have to differentiate between realism of natural images, that means dogs and cats and chairs and tables and cars, and industrial images. When we're talking about the industrial image, it looks completely different, and the features in there are completely different. So those metrics show they are measuring the same thing as they would in natural images, but that is not necessarily the thing that we want to be comparing to. So number one thing that we are using when generating rule-based simulation is, okay, let's see what the real system produces. Let's see what we have produced. Does it look good? Second thing is, so we are really comparing, okay, does this look similar to us? We are, of course, using a number of metrics, mathematical statistical methods that allow us to compare the features, the high frequency, the low frequency features of the image, and to see, does this correlate? We are also looking into what is very important is what are the assumptions under which the image has been created. And here we are coming to the digital twin. So the digital twin is basically this whole system behind the synthetic data generation that allows you which light did you use, which camera did you use, what were the parameters. Given that your simulation is correct, you have to choose the right parameters, and the parameters need to correspond to the system that is being simulated. You have the possibility there to say, okay, these are my a priori, so to say, realism parameters. Can I make a check? Okay, I have simulated the camera. To which extent is this simulation realistic? I have simulated the light. To which extent is the simulation realistic? And one can always go further and further and further. And with this, it builds us confidence into the data set that we are generating. So it is not only a matter of seeing if the image looks similar or not. It is also knowing, because once you create 10, 50,000 images, you're not going to check every one of them, right? So what you want to do is you want to know that the parameters that you have will create realistic patterns. And I'm not talking only about the surface features, for example. I'm talking about the defects. Because if we are talking in the domain of surface inspection, where defects can be different things, it can be scratches, it can be dents, it can be porosities, bulges, delamination, all kinds of things. We have mathematical models that take defects into separate classes, and for each class, we have a number of physical parameters that control the physical properties of those defects. And based on those models, the stochastic geometry models, we know that our defects are realistic because we have the full control of that. And this brings us then to the point, okay, how do I know that this synthetic dataset will work for me? Well, you have to try it. This is a very simple answer. We have run a number of studies. There has been a number of studies worldwide done showing that synthetic data set can perform as good as the real data set. And then if combined with a small real data set can even outperform pure real data set because of this generalization and capacity of edge case scenarios generation. So there is definitely foundations that say, yes, it will work for you, but you have to try and you have to speak to the professional. I definitely invite anyone who is listening to this to talk to Max or me and to see, okay, what is your use case? What are you struggling with? Where is the problem? What are you trying to look for? And we are happy to give you advice. Okay, does this make sense to use the synthetic data set here or not? I think that is, at this point, the best thing. Talk and try.
Okay, thanks. And are there domains which are more or less saturated with synthetic data generation options, and why?
Yeah, so the synthetic data has been on the rise in the past few years. I would say one of the most prominent synthetic data domain was scene recognition, and in particular, scene recognition for self-navigating vehicles. There is already a large amount of different tools that could be used in this domain. Or another domain is health data. Now there is a different tools, a lot of on different levels. Synthetic data is being created. We are talking from unstructured, structured, tabular data, and so on. But I do know that there is a lot of effort being pushed in this direction because of anonymity, because of the issues with the privacy, with data, with the patient data, and one cannot so freely train the models on the data. And there, the synthetic data gives really the benefit of saying, okay, we have created something that looks like real, but it isn't real, so patients are completely safe. We are now entering then the third phase, where the industry is saying we really badly need AI for different processes, but the problem with the industry, as always, is we don't have the data. Because the first two, there was a lot of data sets. There was a lot of data sets available, public data sets, especially for the first one, for the self-navigating vehicles. There is a bunch of public data sets. But as we are going more and more specific in the domains which are more closed, public data sets are not available, and the chances of training a system from scratch are more limited. So that requires more resources from the customer. So the industry has turned out, okay, we need the data. We need the industrial data sets. They are not available. What can we do? Synthetic data. And this is the point where I see that the most of the industry is so far has been focused on, again, scene recognition, because it requires realism on the domain of geometry. So when we are synthesizing an image that has to show the whole scene, you do not have to make sure that every scratch on a surface is physically correct. However, when we go into more specific and more detailed views, such as inspection, quality inspection, there the synthetic data has a really large potential, and there is only a few providers that can provide a solution good enough for this kind of domain. So there I see a lot of development potential in the next years.
Oh, thanks. Maximilian, recently Fraunhofer ITWM has decided to join forces with your company Medabsy. What are you focusing on, and what will this cooperation bring to the market?
Yes, and we are really happy about it. Yeah, the thing is, we are a small startup, and yes, we did some projects, but it's like machine vision. There are projects that are really, really difficult, and we can't do it because we are too small. And synthetic image and digital twins make only sense if you have really high realistic synthetic images as a result. And this is the reason why we want to work with Fraunhofer ITWM, because they have the complicated mathematical models, which allows you to make synthetic realistic images in, for example, especially in the metal surfaces. And we said, hey, let's join forces together, because on the other side, the benefits of a startup is we're trying to to offer our customer as fast and as easy as possible a product so our customers can use it and get the synthetic images. So it means on the one side we make the web browser platform which is easy to use for our customers to get to generate themselves this twins and images. And in the background we are using the Fraunhofer ITWM. And what we are doing now at the moment is we attending it's called AHEAD program. This is from the Fraunhofer Ventures. It's a program which helps the research institute or also startups for the technology transfer. So the transfer from the institute to the startup. And this is what we are doing at the moment. We are also posting on LinkedIn. So if you like to know more about it, you can follow us on LinkedIn. And yes, and this is what we are doing at the moment. We are really happy, and we like also to work with you, Petra. This is it's a really good time, and we're really, really happy about it.
So, Petra, Maximilian, thank you very much for being part of our podcast. And to listeners, if you're interested to get more information about both, you will find the homepages and the links at the commentary of our podcast. Thanks and bye.
Thank you. Thank you very much, Peter. It was a pleasure.
Thank you. Bye.
If you would like to find out more about inVISION, please register for our inVISION newsletter at invision-news.de/news. Become a follower of our LinkedIn channel, inVISION News, or find out about our webinars at invision-news.com/talks. I look forward to welcoming you to our next episode of our inVISION podcast, 5 Questions Too.